What's up, y'all? We're here in Austin, Texas at Aalo with Matt, the co-founder and CEO of Aalo. Let's take a tour of the facility. Let's do it.
Yeah. So welcome to our factory. Here we are mass manufacturing not just nuclear reactors, but nuclear power plants.
Wow.
So in here we are making the reactor vessel, a bunch of other components, and also the civil structure that'll go towards these small purpose-built power plants to power AI data centers. So that's what we're doing in here. Let's go through section by section and check it out. There's something. So this is the plate rolling section. So this is where we make the big vessel. And you're gonna see the finished version over there, which is this gigantic kind of 20 feet tall, 10 feet diameter vessel. Fits on the back of a truck. And we're going to ship 5 of those to each site to make one pod. So a pod that powers a data center, each one is 50 megawatts. And that's kind of very intentional because the average kind of building block of a data center, they tend to get built out in these 50 megawatt chunks. Okay. So our product is not what you see there, it's not the reactor. Our product is the whole plant. And that each plant is called a pod. So that's 5 reactors, 1 turbine. And the reason for that is there's a high level of redundancy. So in other words, if one reactor is down for refueling or maintenance, the others can remain on and make up the delta. And you can have power around the clock, which is really great because data centers need power all the time. Okay. And kind of a big part of the idea here is we're going to be able to do, if customers desire, a fully off-grid solution. So this would be islanded from the grid, which is really nice because it saves time, because interconnection queues are really, really slow and long. And it saves money because often T&D, transmission distribution, is half the cost of delivered electricity. So having something that's on site, that uses a very small footprint, that's co-located with the data center, is a really, really kind of sleek value prop for these data centers to power AI. So
that's dope. How large is the reactor, like it's going out to these data centers?
So the reactor itself is 20 feet tall, 10 feet diameter. There's a finished one over there you can see. And you'll imagine there being 5 that are kind of side by side in a row, and it's going to share refueling equipment, it's going to share operators, and share a bunch of the kind of OpEx that goes into running a power plant.
Dang. And those 5 can have enough energy to power an entire AI data center, which is, I mean, that's like absurd how much energy that takes, but that's just 5 of those can do that.
Yeah, so each reactor could power 10,000 homes. And so a whole, Aalo pod could power 50,000. So generally data centers, they kind of get built out in these 50 megawatt chunks. So there are some that are 50 megawatts, some that are 100, 150, 200. And if you're a hyperscaler, you're going to be building gigawatt scale data centers. But kind of the cool thing is our solution is very modular. So it's kind of the same as a data center itself, right? You've got the GPUs, and then the racks, and then the rows, and then the wings, and then the building shells. And then you've got a bunch of those stamped out. So that's why the solution kind of fits so well, because it's this modular thing that's right alongside the data center and just gets scaled out with the data center.
Wow.
Damn, dude. That's sick.
So you said one of these can power 10,000 homes. Is there any neighborhood that's looking to buy one to just put right in the middle of the neighborhood, power all the homes?
I was like Mueller in Austin's it'd be perfect for there's 10,000 homes there.
Yeah. So one day I think we will do that kind of thing where there's a bunch of kind of small communities in Texas where I don't know if it's quite 10,000 homes, but there's the smaller clusters of homes. And one thing that's kind of cool is you could actually do both the electricity and the heat for those homes. So basically, even after our heat is used to produce electricity, there's still quite a bit of heat left over that's usually just rejected into the environment. And in theory, you could actually just co-locate this with one of these kind of communities of homes and pipe that steam, that kind of hot water to just heat the homes and offer heating for their air and their water in the homes. Yeah, it is funny because a lot of things in nuclear actually, you do really require kind of special grade materials.
Yeah.
So for example, in the early days of nuclear, there was a bit of a zirconium supply chain, but it turns out you needed super, super pure zirconium to actually use in these reactors. So our forefathers in nuclear basically had to spin up entirely new supply chains from scratch with insanely pure zirconium and other materials for use in nuclear reactors. So yeah, often this is part of why nuclear is sometimes more expensive from a capex perspective, because a lot of the materials are just kind of more precise, because you're doing things at a atomic level, and every neutron counts.
Yeah.
So it's kind of different than when you just put in some hydrocarbons, burn it, and use that heat. That's kind of a messy, sloppy process. Nuclear is very precise. And that's also why you want these plants to last a long time. So a lot of some nuclear advocates call nuclear power plants these kind of energy cathedrals, because the whole idea is you can actually refurbish the components that get a lot more wear and tear and make these things last for like 100+ years. So you can keep refurbishing it and always use it as we should, because it's clean, baseload, super safe energy. So yeah.
How long have y'all been in this facility, this warehouse?
So we moved in about 5 or 6 months ago.
Okay.
So this was an empty shell back then.
Wow.
And what you see now is around 80% complete. So we're going to be in 4 weeks unveiling the finished reactor prototype.
Okay.
And the finished pilot line for the factory.
Nice, dude.
So yeah. So this machine over here, this is the water jet. It gets used a lot. If you talk to people, with factories, like often they have a ton of machines, but the one that gets used the most is most often the water jet. Super multi-purpose, can cut through very thick metal, and basically the way it works is you're shooting very high pressure water with some kind of particulate, so some matter in there that adds some inertia to that beam of water, and it cuts through things with pretty good precision, very thick. So it's a very handy machine. So this is a CNC machine, the mill. This is a CNC lathe. So it's kind of cool. I was touring my parents around the factory, and my grandfather was a woodworker. So he was an immigrant to Canada and Winnipeg, and he did a lot of lathe work, making kind of little wooden posts for furniture and things. So when I showed my parents this machine, they kind of got emotional, because it's like, I never met my grandfather, but I think he would have been proud of what we've been doing here.
I bet, dude.
That's really cool.
So yeah.
Dang.
That thing's massive. It looks brand new.
Yeah, some of these are used, some are new.
Yeah.
Do you guys ever get a machine in that you're like, I have absolutely no idea how to use this, but then you're like, you figure it out? Like, because these are all, there's so many different components, I feel like, to what you can build in each of these machines.
Yeah.
Or is this just like your wheelhouse? Is stuff you already have known about and like have dreamed of bringing into the office?
You got to hire the best people in the world across a whole wide swath of parts of this puzzle.
Yeah.
So it's like manufacturing, finance, product, commercial, nuclear. That's I think the name of the game. It takes a village to build a reactor.
Yeah.
And we've tried our best to bring on an incredible team across that whole kind of spectrum.
What do you say to people to like sell that vision to hire the best talent?
Well, I think it's a bit of a snowball effect, because I think like the best talent attracts other great talent, and I think if you're able to show that you're putting together a fantastic team, it becomes easier and easier to attract amazing people, especially if you're working on a really meaningful mission.
Yeah.
And I think it's going to take many years to pull off what we're trying to pull off, and as long as we are able to put together a really solid plan that just really makes sense and holds up to scrutiny, then I think that helps to attract amazing people, because it can be pretty obvious when a plan falls apart. And I think if you put together the right plan, the right people, you can pull off a lot.
Yeah.
I like that. It takes a village to raise a reactor.
Yeah, exactly.
We've all heard that one before, right?
Yeah.
So yeah, apparently this is the most dangerous machine.
Okay.
This is for bending. It's very simple. You put in a big sheet of metal and you bend it. But sometimes it catches people off guard because it kind of catches something on your clothing or a finger or something. So be careful if you use this machine.
Wow. How much is that machine worth?
These are all like kind of low six figures.
Yeah, low six figures.
Low six figures.
Yeah.
Whatever
Someone's
that means.
pre-seed around.
Okay, so this is our welding station. So we have you'll see like a large turntable for welding, which is where we're going to do our larger vessels, and then some kind of hand welding stations to do the smaller components. So these are called downcomers, and essentially there's going to be a couple of these in that reactor vessel, and it'll be kind of in the lower half. And this is a loose fitting, which is because we're going to have this big insertable kind of contraption that will have the pumps, the heat exchangers, a lot of the top componentry. And the idea is you want to easily be able to insert and remove that thing for maintenance and refueling and things like that. So you can imagine these three things in a big triangle and then inserting this gigantic thing into it.
Yeah.
It loosely fits. And the reason you don't have to weld it is because we're doing a hybrid design. So it's kind of like a mixture of like a pool type and a loop type sodium reactor, where you've got coolant being forced through these channels, but it doesn't matter if coolant leaks. It's in a pool of more coolant. So that's just basically to make operation easier, make it safer, and just simplify across the board. But the one kind of core thing that hasn't been done for these reactors before is mass manufacturing them. So if you look at the history of nuclear, like it's usually been the razors and blades model, where people like sell these reactors kind of at cost or at a loss, and then make money by like servicing, refueling, maintaining.
I see.
But there is one reactor that actually did make margin on the sale of the reactor. It's the trigger reactor, which was this kind of small research reactor. And they made 66 of them, and they actually made margin on the sale of this reactor.
Wow.
So it's like, if you want to make margin on something, you got to make it a lot in a factory, the same thing over and over again. And then also, like this kind of helps solve one of the main pain points for nuclear in the West, which is, it's actually not the regulator. Like, a lot of people think, oh, the NRC is the reason we don't have more nuclear. Could the NRC be more efficient? Yes. But there are 8 utilities that have approved licenses to build AP1000s, and they're choosing not to because of a fear of insane cost and schedule overruns. So what better way to resolve these crazy overruns than mass producing something in a factory where you know exactly how much it'll cost and how long it'll take, so you've done it 1,000 times before. That's what we're trying to do.
Damn, dude.
Is this the gigafactory, or is that something that's still to come for Aalo?
Yeah, so this is our first factory, but what's kind of cool is it could also be a gigafactory.
Okay.
Because the goal here is to produce 100 reactors per year.
Got
so
it.
each one
Wow.
is 10 megawatts, so that is a gigawatt per year.
Dang.
So it's
That's
technically
crazy.
it's a gigawatt factory. Right?
Technically.
Nice.
Yeah, so don't look directly there, but there's some welding happening. And then
I want to look. I want to look.
My eyes.
Oh, it's actually so bright. I looked. Yeah, I
oh
looked.
no.
Now you're gonna be
Like a
blind for
little
the rest
kid.
of the interview.
So yeah, this is our circumferential welding station. So we got a robotic welding arm. We're going to be putting the pressure vessels, or the reactor vessel on here and welding as it kind of rotates. And this thing is very precise. You can do a lot of automated movements and kind of increase throughput in an automated way. But again, this is just the pilot line, and a lot of this will change as we kind of approach criticality and building that first reactor.
Yeah.
But kind of like the main thing that we're trying to do here by having such an early focus on manufacturing is having all that information feed back into the reactor design at this early stage. Because like oftentimes people start going down this reactor designing pathway and they kind of forget that like you got to think about how to mass manufacture it from the beginning.
Right.
If you don't have that feedback loop, then it'll kind of make life challenging for you down the line.
For sure.
Yeah.
What is the timeline for having your first fully built nuclear reactor?
Tomorrow.
Really?
Actually? No, well,
Oh.
that's the first non-nuclear version.
Okay.
And we're going to have that done in the next few weeks.
Okay.
And we're going to dig a 30-foot hole. We're going to put this vessel in that hole. And we're going to be basically recreating a lot of the world's most famous sodium leaks and showing that we can resolve them in a matter of minutes, not months or years.
Dang.
Okay.
Because like
That's sick.
the whole thing with sodium reactors is like there's kind of this graveyard of a bunch of groups of people who thought sodium reactors would be this holy grail of economics. And the reason for that is because it's much more compact. And it saves some of the safety systems because it's at atmospheric pressure, versus a pressurized water reactor. It's high pressure. You've got a lot of hydrogen in the water that can dissociate and maybe cause a safety challenge. So that's why sodium is nice, but the thing is it's very leaky.
Okay.
So if you're able to easily patch those leaks or prevent them, that's the big kind of maybe equivalent to us like landing a rocket. It's our big engineering challenge is how do you rapidly plumb a leak, basically.
Sick. All right. Yeah, that sounds great.
So this is our first fuel assembly that we made. So if you look at the bottom, that's where the liquid metal flows through. It's the bottom,
Okay.
and it gets forced and kind of gets heated, and it rises up through all the fuel rods. This is also the control rod is inserted in the fuel assembly. So in this system, we're doing a lot of repetitive stress testing and testing various things about a scram, which is where you basically let the control rods just drop in due to gravity in some kind of emergency scenario, shutdown scenario. So yeah, that's a fuel assembly.
Cool.
Wow.
And then let's go.
Do you have any uranium here at the
We do not.
facility?
I don't know if you guys would be allowed in. Yeah.
When does
That'd
that
be
happen?
so sick though.
It'll get fueled somewhere else.
Okay.
So everything here is non-nuclear.
Got
It's
it.
a lot of stainless steel, a lot of metal.
That's reassuring to hear.
Yeah. So this is the reactor vessel. So you can imagine the nuclear core will be kind of half this height and maybe like this kind of big. They'll be down there.
Wow.
And that vessel over there is where the liquid metal will be flowing in through those downcomers over there.
Yeah.
So those pipes will be connected to those 3 holes you see, and liquid metal will get pumped through the bottom, and the core will be over that kind of cup. And then a lot of the pumps and the heat exchangers and things like that will be up here at the top, and it'll be easily kind of loosely fitted, like I said, just kind of inserted down. And you can imagine this getting extracted during a refueling operation, and then the robot arm will come in and kind of shuffle the fuel assemblies. And there's going to be around 18 of those things.
Okay.
So you can just kind of see how it all comes together in the next few weeks. Initially we're selling this to customers who have a really strong need for power that can be clean, baseload, on site, and rapidly deployed. And so, initially the power prices might be a bit more expensive, but that's okay because for a lot of these data centers, they have a pretty high willingness to pay because they can make so much money with this power.
Got it.
And if you can offer a solution that allows them to go faster in a clean way, that's worth a premium.
Yeah.
And so that's what we're trying to capitalize on.
Got it. Okay.
Just want to show you guys some things down here.
So do you think there is a timeline at which people would have a nuclear reactor in their house somewhere? Is that even
like the Enron egg?
Yeah,
like we were just talking about that with Nifty.
Yeah.
I was like, that bullshit is a gas, not real,
no,
dude.
Yeah, it doesn't make sense to put nuclear reactors in homes.
Okay.
Because kind of the minimum scale that makes financial sense is like a megawatt, and the average home uses a kilowatt.
Got it.
So it's like 1,000 times still too powerful. Maybe you do a megawatt for 1,000 homes. So I think what might make more sense is you do like little reactors for those Texas communities, right? That does power and heat for that community. But it doesn't really make sense to have a reactor in your home. So this is a hydriding furnace. So this gets very hot, and we get hydrogen that comes in, and the H2 molecules dissociate into protons, and they work their way into the metal. And one thing that's pretty cool is if you have the equivalent volume of water, there's actually more hydrogen in a metal of the same volume than water. So it's kind of cool. You can actually store a lot of hydrogen protons in there.
Okay.
So that's that. And then this is a crucible to melt down zirconium. So this is kind of how we're going to make our moderator, but this is just lab scale testing. But yeah, our moderator is zirconium hydride. So it's this very, very pure form of zirconium, along with hydrogen atoms that are what do the moderation. So yeah, in a moderator, you basically you got neutrons flying everywhere, and you know how if you have billiard balls, if 2 billiard balls hit each other, they slow down more than if it hits a wall. It kind of keeps its speed. So you want 2 subatomic particles that are roughly the same mass and size, which is a proton and a neutron. So that's why protons, like hydrogen, when it's in its atomic form, is such a good moderator, because it's the same size and weight or mass as a neutron.
Sick. Wow.
Yeah.
All right.
Getting a full crash course in chemistry and physics right now.
Yeah. And so this is our sodium test. So our initial super small scale sodium testing we were doing. So we did this at Prototown, which is a nearby kind of site for scrappy testing. And so what we have here is an early test of 4 different types of leaks. So basically, sodium, when it's heated up and it's in liquid form, it's roughly like water in viscosity and density. So super, super leaky, which is surprising for a metal, right?
Yeah.
But we've got different types of leaks. So this is called a double guillotine break, which is when you assume that someone takes a samurai sword and slices through your pipe. which if you ask me is the least likely form of break when the regulator wants you to consider it. And there's a few other types of leaks. This one is a cracked pipe. And so this was one of our earliest tests to get good at dealing with leaks of various types.
What is like the, so when people hear nuclear, they're thinking Chernobyl. So what is a leak theoretically like? What's actually going to happen if there was a problem like this at a reactor?
Yeah. So the history of sodium reactors, there's never been an explosion because it's low pressure. It's not something that would really drive that.
Yep.
But sodium does smoke if it gets out into the air, and it can catch fire.
Got it.
So it's basically like an operational challenge for the plant itself. The main thing with sodium is you want to prevent it from getting interfacing with water.
Do you want to head back inside and sit down and have a further conversation about what's next for the company?
Yeah, let's do it.
Welcome back to the show. If you're watching this, we just saw an incredible tour of the Aalo facility. We're now back with Matt here at the office, and excited to hop back into the podcast.
Yeah.
Thanks, man.
Let's do it.
Matt, tell us about what Aalo does.
So Aalo is attempting to mass manufacture nuclear reactors that are purpose-built for data centers. So that kind of means a few different things. So it means something in terms of the scale of the reactor. So it's a 10 megawatt reactor, but it also means something about how the whole plant comes together. So we're not just making the reactor here; we're also making the entire plant. And the whole plant we're calling the Aalo pod.
Okay.
So this is a 5-reactor configuration with 1 turbine. And the reason for there being 5 reactors is because if one is down for refueling or maintenance, the others can make up the delta. So you can have power all the time. And that's pretty important because data centers need energy all the time. And there's a lot of other kind of approaches to this that kind of don't do that. And as an example, like a gigawatt scale nuclear plant, it goes down for refueling every 2 years for about a month.
Wow.
And so you still need a grid interconnect in that case, right? And then you've got things like solar and wind, which require a lot of land. And you got to do overbuilding and storage to kind of firm it up, which adds cost. And that also makes siting challenging if you put that near a data center as well. So that often needs a grid interconnect too. And then geothermal hydro, they're still pretty geography constrained. So the idea is like, this product, the Aalo pod that has the redundancy with these 5 reactors and the 50 megawatts, which is kind of really purposefully chosen to be a sweet spot for these data centers because they tend to get built out in these 50 megawatt chunks. So that's kind of what we're doing. We think it's a really elegant solution for the needs of these data centers.
Yeah. Tell us about the second atomic age and why Aalo and, probably several other companies are ushering in the second atomic age.
Yeah. So, the first atomic age was in the 1950s to 70s. And this kind of surprises a lot of people, but at one point, nuclear actually was cheaper than coal. So it already had achieved this pretty incredible kind of holy grail of economics. And there were a lot of people who thought that nuclear would be basically, the majority of our energy by the year 2000. There was this kind of famous expression, energy too cheap to meter, right? But that is not what ended up happening. And there's a bunch of kind of different things that kind of stood in the way. But we really believe fundamentally that it's actually inevitable that we're going to be using, a huge majority of our energy will be nuclear in the next couple decades. And it's just kind of a question of, what's the best way to go from point A to point B? And, one kind of example here is, oil and gas has brought humanity so much, right? It's really been the main driver behind the whole industrial revolution, really. But the thing is, like, it's kind of ridiculous if you take a step back and you realize, like, all of society is underpinned by these like dead dinosaurs and old plant matter, right? That of which there's only a couple hundred years of supply left. And like a couple hundred years, like for, 7 to 10 billion humans, like we need another solution to help drive this next era of growth. And a lot of people don't realize, but nuclear is as safe as solar and wind if you look at the stats. Okay. And also there's enough material that we can use as fuel to last humanity 4 billion years.
Wow.
So it's not a couple hundred years, right? It's billions. And it's just, it can unlock so much good for so much of humanity. So, basically, so our kind of, top secret master plan, how like, Tesla, yeah, how Tesla had the thing where it's like you start with the expensive car for wealthy customers, and then you kind of go down to the mid-range car, the Model S, and then, the car for everyone, right? So our kind of idea is, well, what if we were to make, initially more expensive, first-of-a-kind reactors for customers who really need it, who are willing to pay a premium, and then work our way down to utility customers to strengthen the grid and build a lot of resilience. I was at a talk yesterday where the power just went out in the middle of the talk. And it's like, this was very, apropos kind of thing. Yeah. And then eventually make this cheap enough to use all around the world, even in developing nations, to lower their cost of energy and make it clean and baseload. And, the whole end goal here is just increasing quality of life for all of humanity, right? And there's that famous chart where basically quality of life is a direct function of how much energy a nation can use. And so if you make it easier to use a lot of energy and do it cheaply and make sure that it's clean so we're not kind of messing up the air that we breathe, then that's, I think, a pretty awesome future to shoot for.
Yeah. We're here in Austin, Texas. This is an American company. Can you give us a little bit of a history lesson on like where we lost our nuclear muscle in America?
Yeah. So there's a few different factors. One of them is that there was a group of kind of hippies who were trying to get rid of both the weapon and the energy source. And they're basically trying to throw out the baby with the bathwater in this case.
Is this in the 60s, 70s?
Yeah, in that time frame, yeah. Okay. And then, at the same time, there was a lot of oil and gas entities, which, not to sound too much like a conspiracy theorist here, but there is
in their best interest.
Yeah, they had a lot of capex that they wanted to kind of keep using. So there's lots of different forces here. And then, I think also, fundamentally, broadly, people's psychology, it took humanity a long time to kind of separate these things in their minds, the energy source and the weapon, right? And it's kind of like they say in Spider-Man, like with great power comes great responsibility. Like if you discover this energy source that's 2 million times more energy dense than the current thing, combustion, like that comes with some major consequences, right? And one interesting example here is, so Edward Teller was one of the people who made the world's most dangerous weapon of all time, which is the fusion bomb. Right? Not fission, fusion bomb. And so, but what's funny is a few years later, he always actually wanted to be working on the energy source. And he also invented the world's most safe nuclear fuel. He invented this fuel called Triga fuel, which is uranium zirconium hydride. It's used in research reactors around the world. Actually, 20 minutes from here, there's a nuclear reactor on the UT Austin campus. And students are allowed to operate this thing, and they can pull the control rods out as fast as they want, and it pulses from a megawatt to a gigawatt in a millisecond, and then it shuts itself off due to the inherent safety of the fuel. So, this has already been invented, right, years ago, and it's kind of cool. Like the same scientists who made the weapon, they always yearned to use this for good. But obviously all the money and the government and the military attention went towards the weapon initially. And again, like people don't realize just how different these things are. Like there are countries that have the weapon, but not the energy source. There's countries that have the energy source, but not the weapon. There's countries that have both and countries that have neither. So these are mutually exclusive. If you want to, if a country has the capital and the ability to make one or the other, that they can do that as they please. So basically, it's a political issue that we have to make sure that the weapons don't get used. Obviously, that's, no one wants to see that happen, right?
Yeah.
But humanity discovered this incredible technology, right? And it can be used for so much good, right? And so that's what we're trying to drive is like, how do we unlock that future? And I think at this point, psychologically, humanity is coming around to it.
Yeah.
And so that's why right now I think the timing is so good to just, let's make this happen.
Definitely.
Yeah.
For those people who are still, they hear nuclear power and they've got fear, apprehension because they're thinking Chernobyl or atomic bombs, what would you say to those people, like as a basic, here is why nuclear power is safe?
Yeah. Well, so there's a few things that, people don't often realize. Like if you look at any industrial process, it comes with risks, right? So When people are installing solar, people can fall off roofs or wind turbines. Oil and gas is already causing a lot of early damage to people's early deaths and so on due to the pollution and so on. And then, for example, the biggest industrial accident that ever happened was not nuclear. It wasn't Chernobyl. It was a dam that broke in China, which instantly drowned 200,000 people. So it's kind of, I think there's like a bit of a getting caught in the crossfire here of people's perception of nuclear, because when they hear that word, they think of the weapon. And obviously that is just, a devastating thing. But the energy source is just so different. And, there's lots of ways to look at this. I mean, there's a pretty morbid statistic, which is deaths per kilowatt hour produced.
Wow.
So it's like, for every unit of energy you produce, whether it's hydro or solar or nuclear, how many deaths result, right? And if you look at that chart, oil and gas is by far more dangerous. It's more deaths per kilowatt hour. And if you come down and you look at nuclear, it's sitting right next to solar and wind. So a few things that surprise people is like in the past 2 meltdowns, Fukushima and 3 Mile Island, there were 0 deaths. Right. That's kind of surprising. People think of those things as crazy. There's a tsunami that killed people in Fukushima, but no one died from that radiation. Some people did die from having to relocate, and there's a lot of controversy over the right approach to have happened there. But it was a tsunami ultimately, right? And then 3 Mile Island, nobody died. And in Chernobyl, so there were 45 initial deaths, largely the firefighters who went in there. That was a very outdated design as well. It didn't even have a containment dome, right? And then there was a few thousand people whose lives were shortened by the time they were 70 or 80. So, obviously you want to avoid that as much as possible. But the key thing is you have to take a holistic view on this. And right now, there are people who are dying because we're not using nuclear, right? And that is what we want to resolve. We want to optimize the least deaths for all of humanity. And it might sound counterintuitive given the perception of nuclear, but actually the way to save the most lives is with nuclear. One more cool thing on this is, so people don't often realize that the main way that we solve a lot of cancer cases is with radioactive isotopes. And the only way to make those, or the main way at scale, is in reactors. So one of the reactors in my home province of Ontario back in Canada makes a lot of the isotopes that's used around the North America. And it actually saves thousands of lives every year. So, if you look at that, it's actually net positive on life, not negative like a lot of other things.
So oil and gas produces maybe the most deaths compared to other energy sources, right? Are there any oil and gas companies right now trying to shift their focus to nuclear, or are they just sticking with oil and gas?
Yeah, there definitely are. So, we're seeing some of the oil and gas companies investing in nuclear in different ways. I think there's also less stuff happening behind the scenes to push back on nuclear, because I think there's just too strong of a groundswell right now, and all of civilization for the most part wanting more nuclear. Even in Germany, which is one of the kind of most anti-nuclear places in the world, they're kind of taking a pivot back now with their new political situation there to get back in a pro-nuclear mentality. Because they turned off their nuclear plants in the past 10 years, and it really hurt their economy because their energy prices went up and they had to burn a lot more coal to make up the delta. So I forget what your question was now, but
mainly are there oil and gas companies shifting to nuclear? But actually, I'm curious, why would a country be so anti-nuclear in the case of Germany?
You should interview Mark Nelson about this. He's got a lot of hot takes on this. I've researched it a little bit. I don't have like the greatest sound bites on this, but like, I think it's largely cultural. And there's some really complex, like, countrywide psychology happening in Germany to drive those decisions.
Interesting.
Yeah.
What is the government red tape here in America around nuclear right now? And what are you facing, like, personally as Aalo to be able to like get your product out there?
Well, so the government has been doing a lot to be more supportive. So there is this thing called the Advance Act, which is meant to make it a lot easier to deploy nuclear in a safe way. So as an example, they've mandated now that you have to spend at most 2 years with the NRC, and they won't take longer to give you a yes or no answer on your design.
Okay.
There's also word about them slashing the cost in half for the NRC.
Okay.
So right now, the NRC, the U.S. nuclear regulator, they charge you per hour for reviewing your design. And, they're not in the business of making money, but they're not exactly in any rush. If they make more money,
They'll take their time.
the longer they take, kind of thing. That's one thing, is having those costs will be nice. And then, there's also things like that we think will have to happen to really unlock this kind of mass manufactured nuclear situation. So, for example, if you go through the whole rigmarole of getting a reactor approved, and then you want to install another one, you shouldn't have to start that whole process from scratch, right? If it's the same reactor, basically, if like the main change is the environment it's installed in, then maybe there's just some review of those different unique environmental characteristics. Right. But otherwise, maybe the licensing for the site, instead of being a whole new 2-year process, maybe it should be a few weeks or maybe a few months or something. So that's one. And then another one is around the environmental, like the air quality type stuff. So that's NEPA. And the interesting thing there, I'm not going to make any bold stance on this, today, but I'll just lay out some of the facts, which is nuclear plants are held to a much stricter standard than any other technology. And I'll give you an example. So basically, there's a limit, which is 10 millirem per year. And if you do the math on this, this is around 1% of the amount of radiation that would cause any measurable impact on human health. And by that, I mean, when you're 70, maybe it shortens your life by a week or something. So it's 1% of that. And other technologies like oil and gas, like they're held to a much looser standard. It's not quite apples to apples, but this is the reality we find ourselves in. So, I think one of the big things that might happen in the next 50 years is we should ask ourselves, like, what does nuclear look like when it's regulated optimally? And one other really stark example of this is if you go to a gigawatt scale gas plant, right? There's like 20 staff. There's a badge keycard system, and they're powering 1 million homes. If you go to a gigawatt scale nuclear plant, there's 400 staff, and 200 of them are armed guards. And there's like 7 snipers in towers, So it's a very different system. And you kind of ask yourself, why does it have to be like that? I think, in the next 50 years, I think that might, I'm kind of an optimist. So I think on that timescale, humanity will be able to right size the regulation. Should it be stricter than, burning a hydrocarbon? Yeah, probably. But should it be that much more? We'll see. I don't know.
So what would our nation look like if nuclear was regulated optimally?
Well, that's a pretty fun question because, let's imagine that nuclear. So let me take a step back. So oil and gas is pretty cool because it's very low capex, very low upfront cost, and then it's much higher OPEX, ongoing cost, because it's like this beast that you got to constantly feed a crap load of hydrocarbon fuel to, right? It's this animal that has to be constantly fed, and the mining of all that fuel, that food for that beast, and transporting it constantly in huge amounts, then it gets burned and goes into our air. Like that's what we're doing today, right? And you can imagine, well, okay, what if you, instead of building a cheap contraption to burn a huge amount of expensive stuff that's dirty, what if you built a bit of a fancier contraption that you could then just load up every 5 years and never load and just, nothing in between, and it's clean baseload energy that whole time? Like that seems like a much sleeker solution. And interestingly, part of what dictates what gets built in the energy infrastructure space is how the financials look. And it's kind of more attractive if you can make something that's lower capex, because you can get a payback sooner and so on.
Yeah.
So I like to say that like nuclear is kind of like a civilization scale marshmallow test. You know, that kind of thing where like there's two kids and like you get an extra reward if like you get like an extra marshmallow if you like wait longer to eat your first marshmallow.
Yeah.
Right. It's kind of like that where, you know, it's ultimately better for humanity to do nuclear, but one of the blockers today is that higher capex. So, you know, to come back to your question, right? It's like, imagine a world where nuclear had the same capex as oil and gas, but then had as low of an opex as it does today. That would be insane. And that's where you can get to, you know, potentially energy too cheap to meter kind of thing. It's not free, but it's like going to be, you know, much cheaper, maybe like 1 to 3 cents.
Are the globe's clean energy goals possible without nuclear energy?
Well, I'm pretty biased, but I would say no. Yeah, I mean, so you know, the thing is, like, humanity can do whatever it wants. Like, humanity could, you know, build everything out of gold. Humanity could, like, you know, which would be the question is, what is the optimal solution, right? And you know, if you built everything out of solar panels and batteries, I think it's a suboptimal solution because you're going to use a lot more land, a lot more material. And, you know, if humanity keeps growing, there's a certain situation in which you'd have to like be covering entire continents in solar panels. And so, you know, I just don't think it makes sense to do that. Solar is really cool in a lot of cases. And there's a lot of surface area we could be covering with solar panels, like on roofs and things like that, you know, would be awesome. But, you know, there's just so much nuclear energy available to us and it's such a compact, clean solution. I think it should really be a major part of that picture.
Yeah. So Aalo is building in the next year. It sounded like you guys are going to build 100 nuclear fission reactors. Is that correct?
No,
or
so
in a goal or in a year you can create.
Yeah, so our eventual goal is to be able to do 100 reactors per year in this factory.
Okay.
But you know, we're not doing that this year. So yeah, this year we're finishing the non-nuclear prototype in the next few weeks. We're installing that in a site in Texas, and we're going to do a lot of non-nuclear sodium testing.
Okay.
In parallel, we're still pushing towards getting approval to build our first real reactor. Next year is our internal target.
Okay.
Not making any promises, but next year is our internal target. And then commercially shortly thereafter.
Okay.
So, yeah.
So who is the customer? Who is getting 100 nuclear reactors?
So yeah, we want to basically really focus on the factory making a lot of reactors and selling them to partner developers. So for the first reactor, you know, we're probably going to have to own and operate that ourselves because who else would want to own and operate someone's first reactor? But after that, we're going to be like, okay, let's sell as many of these as possible to these partner developers who are deploying, you know, data centers and eventually lots of other types of energy consuming things, like, you know, desalination plants or you know, part of the grid, that kind of thing.
Yeah.
There's a lot of new chip manufacturing plants, I feel like, happening here in the United States here pretty soon. Is that a giant target for y'all? Or a future customer for y'all?
Yeah, definitely a future customer, definitely on the radar. There's also, you know, we'll see if the quantum computing kind of announcements start to become more real as well. So Microsoft's been making some cool announcements there, and we'll see how that unfolds, but that could be also pretty power intensive. So yeah, there's a lot of cool possible target markets for this technology.
Ballpark, how much does a nuclear reactor cost?
So traditionally we're talking billions,
Okay.
but because these are smaller and, you know, they're more targeted at, data centers. So the ballpark for this is going to be more in the hundreds of millions.
Okay. Wow.
I think Josiah's point is right. You know, when you think of nuclear, people's mind, right, just goes straight to Chernobyl or, you know, these catastrophic events. How do you change the public's perception around this kind of energy? Is it re-education? Is it through marketing campaigns? How do you go about that?
So I think, you know, first of all, there's been a lot of awesome advocacy for nuclear on social media and in the press and things like that. And, you know, I'm an optimist. I am an optimist. So I think that in the long run, the truth kind of comes out. And so, you know, it's almost like, when Tesla was new, and there was like this hidden secret in plain sight that EVs were so fun to drive, and everyone who drove one became a huge fanatic. You kind of see that in nuclear right now, where a lot of people who have looked into nuclear kind of realize how incredible it is, and then they want to go spread that good word, and that's been a huge groundswell for nuclear. I also think, as nuclear becomes more widely deployed, it'll intrinsically help to kind of build a lot of public support for a few reasons, right? One is familiarity. So if you see something all around you all the time, it's human nature, you get more used to it. And two is, as the workforce gets bigger and more people work in nuclear, then they're obviously going to be more aligned with it and more familiar and support it. It's kind of like, how right now oil and gas is such a bigger behemoth of an industry, and all those people, they don't want to lose their jobs, right? So why would they go against oil and gas? So this is kind of interesting, because if you look at the technologies that translate, that are good things to wean off oil and gas and move on to, with solar, for example, all the jobs right now are in China. They're making all the panels there, and then it's actually very it's not one-to-one to translate from coal, for example, or gas to solar. But if you transition from those hydrocarbon sources to nuclear, it's way more one-to-one. It's still a thermal plant that has all these jobs, and you're operating turbines and all these things. So it's kind of even like a more soft kind of landing pad too. So I think those things are, I think, what will drive way more of the pro-nuclear movement, is both the advocates who are taking that cerebral approach, and then the people who are at these jobs today who want something similar. And I think those things will really drive the nuclear transition.
For the cost of being in the hundreds of millions, how does Aalo get enough funding to even be able to create this mission?
So, I was looking at this stat on a lot of the most successful, even software companies, as compared to the most successful deep tech companies. And at scale, they all kind of required a similar amount of capital. They've all raised, basically billions. And so, for us to reach that escape velocity, we've just been moving as fast as we possibly can. So we're actually just over 2 years old as a company. We're pretty young. So in the first year, we did a 6 million seed. In the second year, we did a 30 million Series A. Okay. And this year, we are aiming to do 100 million Series B. And we think after that, we'll probably do one more private round, which will be a bit larger. And that might be sufficient to get us to either IPO or profitability, certainly revenue.
Yeah. Yeah. What are some benchmarks that you have to hit to reach that Series B?
So with the seed round, we brought on the core technical team and finished the conceptual design. With the Series A, we moved into this 40,000 square foot factory space you guys just toured around. So we finished the factory line and finished the non-nuclear prototype. And then the Series B is going towards the first real reactor. So basically, that'll get us pretty much to criticality, which is pretty unprecedented, right? If we can pull this off, this is all our targets. No promises.
Gotta dream big. You're an optimist.
Yeah. But this would be pretty unprecedented to go from incorporation to breaking ground on a first real, power plant that can power a data center within 3 years of incorporation. That's pretty fast. And so, ultimately, that's what we're trying to do, is just move very quickly. The longer you go, the more money you spend across everything. So if you can optimize for speed while maintaining the high enough quality and safety and so on, then that's, I think, the best shot you have at survival as a nuclear company.
Do you have a plan for what that first nuclear reactor that you guys are going to operate, what that's going to power?
So that first one is called the Aalo X. It's our kind of experimental reactor. Mm-hmm. So we're doing it with DOE authorization at Idaho National Lab. Mm-hmm. And so that reactor is meant to just prove what can be done and be used to validate and verify everything in our plan.
Got it.
But our kind of theory here is there's a lot of nuclear efforts that have been around for 10, 20 years and haven't built anything yet. So we just want to make sure that above all else, we focus on speed and economics and really make sure that we can just get this first reactor built. Because there's too many, anti-nuclear people or non-believers who are like, oh, it's all just on paper, things like that. And, ultimately, like also, there's all these different types of agreements with the hyperscalers and so on, which are all kind of, somewhat toothless PPAs or agreements that don't have real, binding terms. And it's like, none of this will really get real until that first reactor actually gets turned on. And at that point you can say, oh, okay, here's how long it took us to build, and here's how expensive it was. And then you can just get better from there. So yeah, we're going as fast as we possibly can to build a product that is well designed from the ground up for data centers.
We're coming to a close here. What can our audience expect from Aalo this year that they should be excited about, that you're excited about? What can they expect from the company?
Yeah, so this year is all about the non-nuclear testing in preparation for the construction of the first real one, hopefully next year. So, like we were talking in the factory, there's kind of this graveyard of sodium reactor efforts that happened in the 60s and 70s, where they thought that sodium would be this holy grail of economics. And it ended up not being, because they had these operational issues with sodium. So the game plan for this year is to take that finished reactor prototype and bring it to this plot of land in Texas and basically recreate a bunch of the biggest sodium challenges that have happened in the world in the past 70 years and show that we can resolve that in a matter of minutes, not months or years. That's kind of like our equivalent of landing a rocket. It's like, how fast can we just plumb up a leak? That's what'll unlock this awesome economics for sodium reactors. I think so it might be worth highlighting. So with sodium reactors, there's two main things that make it really well suited for good economics. So one is it's very compact. So you can make a reactor around half the size that it would be if it was using pressurized water as the coolant. And the second thing is around safety. So when it's non-pressurized and you don't have hydrogen and water that can dissociate and cause problems, basically your main concern is sodium going to leak, and can you will that smoke, and can you just patch that leak up as fast as possible? So this is what I'm excited about this year, because like that de-risk is a major kind of thing that if we get past that, can unlock a really promising future. So really cool economics, and I think we'll learn a lot this year.